Okay. So the first one, okay, that we're going to go through, okay, is the problem, okay, related to the RLC circuit, okay. So you're asked to find the steady state current, okay, labeled as the IT, okay, in the RLC circuit, okay, where you're provided, okay, with the initial information, okay, R equals to 10, okay, L, okay, 1 Henry, and capacitance of 10 to the negative farad, okay, and then ET, okay, as the function of time, okay, with the unit of volt, okay, as follows, okay, the following is here, and periodic period is given as 2 pi. ET, okay, is provided, okay, as two function of time intervals, okay. The first one, if t is in between negative pi and pi, okay, the first line, ET is going to be negative 50 t square, okay. And while t is in between 0 and pi, okay, the function is going to be 50 t square. So first of all, okay, we need to determine, okay, this steady state current, okay, which is the ODE equations. Okay. So we get this one, okay, L d square I, okay, by dt square plus R, okay, di by dt, and then plus 1 over ci, okay, sorry, 1 over c times I, okay. So that we get, actually this one is going to be dE by dt, okay, but let me label it as E prime t, okay. So first of all, okay, once we need, okay, E prime t, so let me find the function of E prime t first, okay. We only know the function of time, okay, of et, right, okay, the normal one. So if you find the derivative of this one and this one, okay, what we get, okay, would be negative of 100t, right, for the first time interval, and another 100t, okay, for a second time interval. Okay, so the first one is if t is in between negative pi and 0. Okay, and the second one if t is in between 0 and pi. Okay, so get this one. Another one, okay, not another one, okay, next step, okay, would be, well, let we find, okay, the homogeneous solution first, okay, for this one. And let me label as solving for homogeneous solutions. So that we are going to solve, okay, this one, d square I, okay, by dt square, right? I have plus, sorry, we do have L, okay, in front of it. And then plus R, okay, di by dt. And then plus 1 over c times I, okay, but this one we equate, okay, equals to 0. We can substitute, okay, what you are given, okay, as L is 1, right, while I is 10, and c is 10 to the negative 1, so actually 1 over c would be 10, right? So we get the simpler one, okay, as the square I, okay, over dt squared, okay, plus 10 di by dt, okay, and then plus 10I, okay, equivalent to 0. This one, okay, we can use the technique of characteristic equation, okay, to solve for this. Okay, so let me find characteristic equations, okay. So what we get, okay, this one is r squared plus 10r, right, and then plus 10, okay, equals to 0. We can solve for this one, okay. Well, let me use the quadratic equations. So r would be negative 10 plus, this one should be 100 minus 40, okay, divided by 2, a is going to be 2. Well, within the square root you get 60, right? So square root of 60 is 15 times 4, so 2. 2 with the square root of 15, okay, divided by 2. So we get -5, okay, plus or minus square root of 15, okay, for r. So we get two, okay, different r, right? So that our general solution, okay, for oh, actually, okay, we have two types of answer, right? We have homogeneous one and the particular one. Okay, so actually, it can label it as ist, okay, plus ipt, right? And we are solving for this first, okay, through the homogeneous, okay, equations. So we'll get is first, okay, which is going to be e to the -5, okay, t, right? Plus, not plus, okay, but we have c1, and then cosine of -15t, okay, plus c2, sine of 15t. Okay, this one as our homogeneous solution part. Okay, homogeneous part. Okay, and then we need to solve. Okay, we need to solve. Okay, for the particular solution. Okay, so you see the right hand. Okay, that on the right hand, this one e prime t. Okay, this one seems to be linear, right? Okay, so we can assume. So this part, next part. Okay, we are going to find uh the particular solution. So we guess the form of the particular solution, right? So let me use, okay, the linear form for our particular solution, which I can label it as a t plus b. Okay, similar to mx plus c, right, in the linear graph. Okay, so let me compute the ip, okay, by dt. This one is going to be a, right? Uh-huh. And then if you find out, okay, d squared, okay, ipt by dt squared, okay, of course, okay, you are differentiate a, or you're differentiating constant, so you get 0. If you substitute, okay, backward, okay, to your differential equations, so we get what? We will get 0, sorry, substitute back, okay, to this equation. We will get 0 equals to, since this one is 0, right? This one is a, but r is 10, so we get 10a. So we get 0 plus 10a, and then plus 10 times I we assume to be at plus b, right? Equals to, sorry, not 0, but this one, okay, let me write it as dep et, okay, over dt. Okay, so we get 10a plus 10at, right? And then plus 10b equals to det over dt. Okay. From this one, okay, we can do coefficient matching. So on the right hands, okay, on the right hands, we can have, uh, if we compare, okay, with, we need to compare with this one, right? This one. So you get either plus, okay, 100t or minus 100t, right? So that is going to be, I mean, this one, okay, should be equals to plus or minus, okay, 100t. So if you match, okay, the coefficient, okay, we'll get 10a, okay, should be equals to plus or minus 100, okay, plus or minus 100. Yeah. Since this one, okay, should be equals to this one, should be equal to this one. So what we get here as a, okay, should be equals to plus or minus 10. Mhm. And for the constant term, okay, for the constant term, we have 10b, right? Okay, so our 10b is going to be 0. So since we don't have, okay, this one for all the first term is 0 right away. Okay, yeah. So 0, so b, okay, is going to be 0. So that we get from these two, okay, we get that IP or our particular solution, okay, should be, actually we got negative 10t and 10t, right? Okay, it's going to be negative 10t, okay, if t is in between negative pi and 0. But we'll get 10t, okay, if t equals to pi and 0. Okay. And that's how we can find, okay, the particular solutions. Uh-huh. And then we can combine, okay, two of them together, okay, to get the general solution, right? We have each after. Okay, so our general solution, okay, would be IT. Okay, since, okay, we know that IT should be the addition of IHT, right, plus IPT. Uh-huh. So IT here, okay, is going to be square root, okay, not square root, okay, but we have to interval, right? The first one, okay, is going to be E, negative 5t, okay. In the blanket, we have C1, right? Cosine of square root of 15t. And then plus, okay, C2, sine of square root of 15t. And then we need, okay, to add, the first one we add negative 10, right? So minus 10t, okay, in the interval of negative pi to 0. While the second one, okay, we get a similar thing, okay, but e to the negative 5t, okay, and then c1 cosine of 15t, right? Square root of 15, and then t plus c2, okay, sine of square root of 15t, okay. But this one you add, okay, another 10t for particular solution. This one t is in between 0 and pi, okay, and we get this too. But actually, okay, we do have, okay, the constant left, right? Okay, so we can apply, okay, our given, sorry, our initial conditions, okay, to solve for this one. So let me apply initial conditions, okay, to solve this one. So the first one, we know that I0, okay, is supposed to be 0, right? While the I0 by dt, okay, is supposed to be 0 also, at t equals to 0. So at I0, okay, is going to be e negative 0, right? And then we have c1 cosine of 0 plus c2, okay, sine of 0. And then plus 10, 0. Actually, this one could be minus 10 or plus 10, okay, because you get the same value, okay, by the way. You can see that we only have sine of 0 is 0, right? This one is 0, and e to the 0, this one is 1. Okay, so we get only cosine of 0 is 1. So we get only c1, okay, which is equals to 0 because I0 is 0. So what we get is this one, and we get the value of constant, right? C1. So right now, okay, we can reduce, okay, the form, okay, this form into just find that C1 is 0. Okay, so this term, sorry, these terms are gone, right, for both, for two intervals. Okay, but if you apply, okay, uh, if you dip, okay, find the derivative, like you find dit over it, sorry, over dt. This one is going to be d by dt, okay, of I, right? In which I, right now, it is just e negative 5t, and then times c2, right? Sine of negative, sorry, square root of 15t, okay, and then plus 10t. Yeah. So if you compute, okay, this one for the derivative, okay, what we get is, let me get from the right, okay, what we get here, okay, is going to be, actually you get the product rule, right? Okay, and then this one you can just dip normally. Okay, so the product rules, okay, we get negative 5t, okay, sorry, not 5t, but 5, okay, and then e to the negative of 5t times c2 sine of square root of 15t, right, plus e to the negative of 5t, okay, but times c2 with square root of 15, okay, you do the chain rule, right, and then you get dip side, you get cosine, so cosine of square root of 15t, and then you plus 10 at the end, okay, you also differentiate this one. So from this one, okay, we know that d0, okay, should be 0, so we can equate this one, okay, equals to, okay, let me use this one, so di0 over dt, okay, this one we substitute t at 0, right, so we get negative 5, this one turns to 1, right, so we get the c2, and then sine 0, sine 0 is 0 anyway, okay, plus c2 here, and then square root of 15, but this one is cosine, so it's going to be 1, and then don't forget to plus 10, okay, equate equal to 0. So this term is 0, okay, this one is going to be square root of 15 c2, so c2, okay, is going to be negative 10 over square root of 15. So the real general solution, okay, is going to be e to the negative of 5t, right? And then negative, we substitute c2 as 10 to the square root of 15, okay? The term c1 is already gone, okay, since you get 0, right? And then we have sine, okay, of square root 15t. Don't forget to minus 10t for the first one. And then you get a similar things, okay, for the second term, for the second one, sine with the parenthesis of square root of 15t. But this one you add, okay, 10t, okay, for the first time interval is negative pi to 0, while for the second one would be 0 to pi, okay. And so this would be the general solution, okay, for this one. Okay. And so this is going to be the first one, okay, the problem regarding the RLC parameters, okay, and then we solve using the second ODE. Okay. Next one, okay. Next one would be about this one would be about heat equations, okay. So consider a thin, okay, insulated rod of length, okay, L equals to 10 centimeter, okay, where heat conduction is modeled, okay, as this one, okay, in which the alpha here, okay, turns to be the thermal diffusion, okay, given as 0.01, okay, square centimeter per second. Okay. Okay. This one we would like to know, okay, the temperature distribution, okay, or UT, right? This one, UXT, sorry, for T more than 0. Okay. So we are going to find, okay, temperature temperature distribution, which is UXT, okay, for T more than 0. Okay. So first of all, okay, we need to apply, okay, the boundary and initial conditions, okay. So let me apply, okay, the boundary and initial condition. The first one, okay, we know that u 0t, okay, like x equal, starting with x equal to 0, okay, this one we start with 0 Celsius, okay, and then at the end, okay, or it is going to be 10t, right, or at the other end, okay, of the rod, okay, this one is supposed to be also 0 Celsius. Or we can say that ends, okay, both endings of the rod, okay, are kept, okay, at 0 degrees Celsius. And then we have, okay, you x0, okay, or at time equal to 0. Uh, we have 100, okay, and then sine pi x over 100, okay, C Celsius, okay, as our initial temperature distribution. That's what we have, okay, for boundary and initial conditions, okay. So this one, okay, we are going to solve, okay, this heat equation, okay, through what we call the separations of variables. Okay. And let's start with, let me start, okay, with, if we assume, okay, a separable solutions. So let uxt can be written as, okay, let x, okay, and then t. So let me separate, okay, into x and t, okay, separately. And then you substitute this one, okay, back into the heat equation. Your heat equation can be recorded, okay, as cu by, actually it's cu xt, okay, but we can simply write cu by t, okay, equals to alpha, right, okay, the thermal diffusions, and co square u, okay, by co x squared. So what we have here, okay, would be x, okay, and then it's going to be dt by dt. Since we are differentiating, okay, compared to t, okay, so we only have the t, okay, and then we have alpha, okay, and then t. This one is going to be d square x, sorry, d square of x, okay, over dx square. And we have this one. Now we can separate, okay, the variables, okay. So we bring, okay, t together, we bring x together, okay. So what we have here is we have, uh, let me move this one, okay, to the left and then move x to the right. Okay, so we have the, sorry, 1 over t, and then we have t over dt, right? And on the right, okay, we have this one alpha, okay, and then 1 over xt that we are moving from the left. And then we do have d square x, okay, by dx squared. This one let me equate, okay, equals to negative of lambda, okay. So lambda is actually the separation constant, okay. Now let's solve for x first, okay. So for x, okay. So we need to use this one. So we get from this one alpha 1 over xt, sorry, x d square x over dx square equals to negative alpha. Okay, so we can move this one, not really moving, okay, but we can bring this one, okay, to multiply this, to divide this, and then bring this thing back, okay, to add up. So we get d square x over dx, and then plus, okay, is going to be lambda over alpha, and then x, okay, equals to 0. Now let me assume, okay, k squared, okay, equals to lambda over alpha. So we will get d square x, okay, over dx plus k squared, okay, and then x times x, right? That's right, x as a function of x, okay, equals to 0. This one is quite similar to the harmonic equations, okay, so the general solution of this one should be the general solution, okay, of this one, okay, is going to be c1, okay, and then cosine of kx, right? Yeah. Plus c2, okay, and then sine of kx. Okay, similar to the simple harmonics equations. And if you apply the boundary conditions, we get, okay, and the first one, okay, we know that x0 should be 0. So from x0 should be 0, we will get this one 0, this one going to be 1. This term is going to be 0. So we get that c1 is supposed to be 0. Meaning that we get that x, okay, is supposed to be c2 sine of kx. Sine of kx. And then we know that x10, okay, x10 is going to be 0. So from this one, okay, is going to be 0 equals to c2 and then sine of 10k, right? So sine of 10k to be 0. Okay. Yeah. So we will get that k. Let me use as kn. Okay. Kn, okay, should be equals to n pi over 10, right? Where n, okay, is supposed to be 1, 2, 3, and so on. Since actually we know that signs of n pi, okay, in which n equals to 1, 2, 3, 4, okay, you get 0. So we get that xn, okay, actually we can call this one as the eigenfunctions, okay, of x, okay, equals to sine of n pi, right, over 10. Sorry, n pi x, okay, forgot x, over 10. That's for x, okay, that's for x. Now let me solve for t, okay, but let me use this side, okay. If we need to solve, okay, for t, Actually, it's going to be t is here. Yeah. This one is the time dependent equations, right? Okay, it depends on time actually. So we can use 1 over t, okay, and then we do have dt by dt, right, equals to negative of lambda. Okay, so we get that dt, okay, over dt would be equals to negative of lambda t. Okay, this one, okay, the solution, okay, should be tn, okay, should be e to the negative of lambda n, okay, t, right? Uh, in which, okay, the lambda n should be equals to alpha of kn square. Okay, but we already know, right, this one is going to be alpha of n pi over 10, okay, square. Then we can combine, okay, the solutions, okay. The solution of u, okay, in which it is u xt, right, okay, is equals to summation of, okay, from n equals to 1, right, up to infinity of cn sine of n pi x, okay, over 10, and then you times with e to the negative of alpha, and then n pi over 10 square t. And don't forget t here, right? After you substitute lambda n, okay, here. And then we do have some initial conditions, okay, which is uh ux, okay, if you apply initial conditions, okay, we know that at time equals to 0, okay, or ux0, okay, is going to be 100, and then sine nx over, sorry, pi x, not nx, okay, pi x over 100. Okay, and then if you compare with the general solution, okay, in which you equate t equal to 0, okay, so you get, okay, this one is from general solution x0. This one is supposed to be sigma n equals to 1 to infinity. You substitute, okay, t equal to 0, right? So this one turns to be 1, okay? So you're only left, okay, with the x term, okay? It's going to be cn sine of n pi x over 100. Sorry, over 10, not 100. Uh-huh. So if we need to match up this one, okay, n should be equals to 1, right? N should be equals to 1. So that C1, sorry, Cn, okay, should be 100. Okay, Cn should be 100. Uh, uh, this one is going to be 10. Not, uh-huh. So to match up this one, okay, only n equals to 1, right? Uh-huh. So that C1 should be 100, okay? Yeah. And Cn, okay, should be 0, okay, for n more than 1. And that's what we get from this. So that the final solution, okay, and this one is going to be the real final one, okay, is we get uxt, okay, should be equals to 100, okay, and then sine of pi x, okay, over 10. E, okay, to the negative of alpha. Actually, we know that alpha is given as 0.01, right? And then n equals to 1, so we have pi over 10, okay, and then t square t. This one is going to be our final solutions. Okay.